So, does anybody have any questions you would like me, that's going to be annoying. Does anybody have any questions you would like me to answer from the practice problems from yesterday? Go ahead, Farhan. Number 9? Okay. Question 9, we have a 5 centimeter tall object and it's going to produce an image that has a location of 7 centimeters behind the mirror. The phrase behind the mirror in this context means that that place where the light is producing the image is not projectable onto a screen. When you looked this morning at the demonstration with the candle flame, everybody in the mirror, that image was produced on the same side of the mirror as the object. In other words, this is a virtual image. Real images for mirrors are produced on the same side of the mirror as the object because the light can physically be put onto a screen. Because this is a virtual image, we need to be able to figure out that that 7 centimeters, which is the displacement of the image, is negative. So the fact that it's behind the mirror tells you that it's a virtual image. Virtual images are erect, which means that the height of the image is positive, which means the displacement of the image is the opposite. So that's crucial or key to answering this question, is knowing that di is negative. The height of the object is 5 centimeters, and the focal length of this mirror happens to also be 5 centimeters because it tells you the radius of curvature is 10 centimeters, and once again, if this is the center of curvature, the focal length is always halfway between, I didn't do a very skilled job of drawing that, but halfway between the center and the mirror. So if the radius is 10, this is the radius, then the focal length, which is this distance, is half of 10, which is 5. What are we asked to find? We want the magnification, and we also want the type of mirror. So this is actually a challenging question. There's not enough information right now for you to determine whether this is a concave mirror or a convex mirror. They both produce virtual images, but you can't make that decision based on the information. However, we do have these two pieces of information. However, again, we don't know whether the focal length is positive or negative. Now, I do know because I happened to glance at the question, at the answer to the question. But let's just say for a moment that you thought it was a convex mirror. Okay? Let's say you thought the focal length was negative. I'm not saying it is. Let's just say that you thought it was because you don't know what type of mirror it is. So you're just going to say, well, let's try a negative focal length. Let's see what happens. Then you would have 1 over the focal length equals 1 over di, which is negative 7, plus 1 over do. And I would like everybody to solve that for do. So you're going to take 1 divided by negative 5. You're going to subtract 1 divided by negative 7. I want to say negative 17.5. It's negative 17.5. So you end up coming out of this exploration, which started here with your guess that the focal length is negative, by getting do is negative 17.5. But do can never be negative. So this is what we talked about yesterday. You started off with an assumption that it was a negative focal length, and the result of that assumption, the conclusion you arrive at from that assumption, is an impossible conclusion. So in logic, if you assume something to be true and it leads you to an impossible statement, then I guess your assumption could not have been true. That means that the focal length must be positive, and it must be a concave mirror. And I'll talk in a bit about what would have happened if you tried that first. We can write 1 over 5 equals 1 over -7 plus 1 over dO. Again, I think on your formula sheet, the dO is in the first term, I think. Doesn't matter where I put it. So this time what you're going to do is you're going to take 1 over 5 minus 1 over -7 and get very close to 3 when you reciprocate it. I'm guessing it'll be 2.9 something. Okay. So I'm just going to say DI is, or DO rather, is positive 2.9. Doesn't matter what the decimals are. You can keep all of the decimals. So now to determine the magnification, I can go ahead and use the magnification equals negative DI over DO. So I can take that -7 divided by this number and get apparently 2.4. And since the magnification's got nothing to do with this next part. Since the focal length was positive and it led us to the answer, it is a concave mirror. I don't know, if you assumed it was positive first, then I guess you would get an answer that had no contradictions in it, which means your assumption was correct. As far as I can figure out, in a case like this, you can never get two answers that both make sense. It's not going to be possible. Other questions? Go ahead, Zebi. 8? So we have a 3 centimeter tall object producing a virtual image that's 2 centimeters tall. So if it's a virtual image, then the height of the image is positive. Stop and think for a second there. Because virtual images are erect, if the height of the image is positive, the other attribute or characteristic of the image is negative. H and D for an image are always positive and negative or negative and positive. So that means when we say it's 2.5 centimeters behind the mirror, we know DI is 2.5. We also know the height of the object is 3, and we're asked to determine the focal length and the type of mirror. Well, what's preventing us from finding the focal length is that even though we know DI is negative 2.5, we don't know the value of DO. We can't put in anything for DO. Just to drive this point home, we're going to have 1 over F, which we're trying to find, equals 1 over, we don't know, plus 1 over negative 2.5. So this becomes here, our DO becomes our goal at this point in time. If we can find that, then we can find the focal length and have an answer to the question. We can use these three because HI over HO equals negative DI over DO. And of these 4 variables or letters, whatever you want to call them, we have 3 of them. So we can put those numbers in. I will have 2, which is HI, over 3, which is HO, equals negative 2.5, which is DI, it's a negative DI, over DO, and then cross multiply and get what I believe to be 3.75. So you get DO equals 3.75 out of this relationship. And now we can go ahead and find F. So we're going to take 1 over 3.75 plus 1 over negative 2.5. And my mental math skills fail me at this point. I can't do that in my head. So 1 divided by 3.75 plus 1 divided by negative 2.5. This, of course, is not the focal length. This is 1 over the focal length. So I need to take the reciprocal of that. I get a focal length of negative 7.5 centimeters. What that tells me is, since the focal length is negative, it's a diverging device, which in terms of mirrors is a convex mirror. Just check. Yep. Is that okay? All right, other questions? All right, we're going to move on today and continue with optics of light. We're going to be looking at refraction of light. And under the best of circumstances, when teachers teach Physics 20, they already have the option of delving very deep into refraction of mechanical waves or just touching on it. And last year, we were not at the best of times because we were going through these continual school shutdowns and all that other stuff. So the teachers decided to make the curriculum as important for the next level as possible. So your teacher may not have taught you a lot of refraction. They may have taught you a lot. It depends. We're going to be looking at refraction of light today. This is section 30.3.6 in your note package, and we're going to be applying something called Snell's law to describe the refraction of light. So to begin with, and here's where I haven't really decided how deep I'm going to dive into this, but in Physics 20, you were taught about refraction in a very general sense, that when a wave travels from one substance to another substance, the wave undergoes changes. So what do I mean by going from one substance to another substance? The classic example would be a wave on a spring going from a very heavy spring to a thinner, lighter spring. Or you could have a water wave that's going from a deep part of the pool to a shallow part of the pool. Or you could have a wave going from jello to what we affectionately called in my family shaky pig. All of my grandparents were born in the Ukraine, and we ate a lot of Ukrainian food, and there's a food called studnets. Does anybody know what that is? It's sometimes called head cheese. And it's called head cheese because you would make it by taking the head of a pig and boiling it, but my grandparents didn't do that. Basically what you do is you take pork and you boil it with flavoring and garlic, and you put gelatin on it. I hate the stuff. It repulses me. And we called it shaky pig because you would let it set in a pan, and then you'd cut it into squares, and they would put it on the plates. They'd have a plate of this stuff, and I know people are giving me that look. That was my look. And it would be passed around the table, but the stuff would be shaking all the time. So we called it shaky pig. So if you had half of a pan filled with shaky pig, which is a really dense gel-like substance, and half of a pan filled with just regular jello, and you had a wave go from the jello to the shaky pig, the wave is going to change because of the properties of the substance. That change is called refraction. And I'm talking here about mechanical waves. So I'm not talking about electromagnetic waves yet. When you have a wave that undergoes refraction, it will always experience a change in its wavelength and also in its speed. Okay? And I will tell you right now that if the wavelength of the wave decreases, the speed will decrease. Okay? So if the wave ends up going faster, the wavelength will be longer. And you know, that should kind of make sense to you because the wavelength is produced by dropping disturbances in the medium regularly. Okay? If the wave is dropping disturbances regularly, but it's moving faster through the wave, then the next disturbance it creates will be further away from the first one, so the wavelength is going to be longer. And what goes unsaid here in your notes is what I'm going to put right here for you. The frequency is the same no matter what. This is the analogy that I would use in Physics 20. We're going to imagine creating a wave, but the medium is going to be people. And we're going to take a whole bunch of kindergarten students and line them up, hand to hand. They're going to hold hands. We're going to have about 8 or 10 kindergarten students. They're going to be a medium that we're going to move a wave through. And then we're going to have the last kindergarten student hold hands with a grade 12 student, and we're going to have 8 or 10 grade 12 students connected. And I'm going to create the wave by going over to the first kindergarten student, grabbing their free hand, and whipping them back and forth really quickly. Okay? And you can imagine maybe they're on skateboards, or they're on something with wheels, or they're on a frictionless surface, so that that first little guy gets snapped back and forth very quickly. But he or she is connected physically to the next person in line. So if the first person is going back and forth, we'll be kind to them twice a second. And they're going back and forth twice per second because the source of the wave, which is me, is causing that to happen. Since the first person has a frequency of 2 hertz, the second person has a frequency of 2 hertz because they're connected to the first person. And the third person will have that same frequency, and the fourth and the fifth, and all the way. And then we get to the barrier between the two media, between the little guys and the big guys. The first person in the grade 12 part of the wave is still going to move back and forth 2 times per second because they're physically connected to the other person that's a little person that's moving back and forth 2 times per second. The difference is because they're more massive and more dense, the wave will go slower through them than it does through the little guys. And I guess maybe what I want to impress on you is this idea before we go on. Not only is the frequency of the wave not affected by the medium the wave is traveling in, but a more dense medium means a slower speed, a smaller speed. Because it actually takes more time for the medium to do that oscillation. It's still making the same number of oscillations per second, but it takes longer, and probably that's because the medium in a more dense medium still oscillates, say, up and down twice per second, but it doesn't go as far. Whereas the other one goes up and down twice per second, but it goes further, so it has to travel faster in the less dense medium. By the way, if it is moving slower, if the wave is moving slower, then the wavelength must be smaller. And again, the reasoning is that the frequency is telling you how frequently you drop a ripple in the medium, how frequently you cause the medium to be disturbed, which is going to be where the start of the wave is, where a crest of the wave is. If the wave is traveling really slow, then it will drop that first ripple, and in the time it takes to get to the next point in time where it ripples again, it will not have moved very far, so those 2 ripples will be very close together. But if it drops a ripple and then half a second later it drops a ripple, but it was traveling really fast, then that second ripple is very far from the first one, so the wavelength is longer. Again, we're talking only about mechanical waves. There's another change that occurs. If the wave enters the second medium obliquely, what does obliquely mean? It means not head on to the medium. Then the direction of the wave will change. So we're going to get away from now talking about seeing the wave in terms of ripples and wavelengths. And I'm just going to say that what we have is a medium. We're looking down. We have a top-down view here. We have a medium, and this is what we call the interface or the boundary between one medium and another. So I don't know what these media are. This could be Jell-O on the left and Shaky Pig on the right. It could be hot air on the left and cold air on the right. It could be kindergartners on the left, grade 12 students on the right. I don't care. That's not my point. When you have a wave that travels dead on, it's going to hit that boundary and it's going to continue. So this arrow that I'm drawing is not showing the wave motion, it's just showing the direction of the wave. What I am telling you is, if the wave hits that boundary at anything other than 90 degrees, then the wave changes direction. So a different wave might travel this way and do that. It changes direction, while the wavelength and speed both change. And the analogy that I use here to explain this for a mechanical wave is one that it's an old analogy. I was taught it in university physics a long time ago. The original analogy, and I'm going to tweak it in a second, says to you that you can imagine what we have for a wave is a whole bunch of people marching. So this is the top-down view of all of these people. And there's lots of them. The classic example in an old textbook from, say, the 70s or 60s would be you have a marching band. And they are all traveling in this direction. But they form a line. There's a line of people here, a line of people here, and a line of people here. Those lines are like the crests of a wave. You can imagine them being a crest. And that would mean that this is the wavelength. So what's going to happen when that first line of people get here? I'll draw another one. So we've got another person, another row, another row, another row, another row. And then you get a person that hits here. And what I'm going to say is that this is pavement. And this is 2 feet of mud. Which, I don't know that you've ever had to walk through 2 feet of mud, but I assure you it's difficult to do. Okay? And what that means is, even though this first person is going to be trying to walk as fast as they were on the pavement, they're going to be slowed down. And that means that by the time this next person gets here, this person will not have traveled as far. And you can already see the line between them is angled differently. It's twisted in. The analogy that I've always used, and I think it makes more sense, is what you have is a whole bunch of wheels on an axle, and it's rolling. And the leading edge of the wheel is going to hit the mud here first, which means that end of the axle is going to be moving forward slower than the end up top. And as a result, by the time it gets in here, it will look like that. This is not something you need to know or even be able to explain. I'm trying to give you a rationale for why waves change direction. So I'm going to show you this visual, and it's a little assaulting to the senses, but I will show it to you. So what we have is a wave. These are ripples on the left traveling in the direction of the blue line. And what happens is the first part of the wave that hits the new medium, which is more dense, gets slowed down before the second part hits, and the whole thing is twisted. So that's an explanation for how mechanical waves change direction and their wavelength changes and they move slower. By the way, can you see that the wave is moving slower in the gray region? You can obviously see that the direction it's traveling is switched, and the wavelength in the gray section is smaller. So this is going from a less dense to a more dense. This line right here is called the normal line. This line here is called the interface. You don't need to write this down, I just want to put it up here. It's called the interface, or sometimes the boundary. And an important visual is that when you have a wave that refracts towards the normal, like if you take a look at this original direction, it's pulled towards the normal. when a wave refracts towards the normal, the wave slows down. Okay? Because it's traveling in a more dense medium, and if the wave slows down, the wavelength decreases. How many of you remember some of this from Physics 20? That's fine. You don't need to. I think we had kind of decided last year that we might talk about in Physics 20 the fact that there's this thing called refraction of waves. Particles don't generally refract, so this is kind of a wave property. And the reason it wasn't that important is we don't care about mechanical waves, we care about light in this course. So what I'm going to tell you now is that light refracts. You have all probably seen that if you have a stick in water and you look at the stick appears bent. You take the stick out, it's no longer bent. That's because it wasn't really bent, it was the light that was bending. Okay? There's all kinds of illustrations of refraction, but I'm going to show you right now, and then we're going to work with this today a little bit, refraction of laser lights. So I've got a blue laser beam, and this dish is circular in fashion. It's filled up with water to the midpoint. Okay? So when I turn the laser beam on, the laser beam is set up in a certain way so that, I'm going to move it up here, so that it's a wide beam. I know it looks very narrow, but what I'm talking about is the beam of light over here is actually a line of light. And that means that it's able to hit the surface behind here, and you can see the beam of light. So what we have is air in here, and the light is going from air to water. So it's refracting towards the normal line. In this particular case, the line that I'm indicating here with my finger is the interface between the two media. Media is the plural word for medium. The first medium is air. The second medium is water. So this light is traveling from air to water. However, this light is traveling from water to air now. The laser light is now on the bottom. And when you follow that beam of light, it hits the interface and it bends away from the normal. Which makes sense. I mean, if you didn't even know that the laser light was down here, you wouldn't know whether it's coming in this direction or the opposite direction. So that is what light refracting looks like. So as a demo, we're talking about this thing right here. We are asked to sketch a ray of the light entering the water from the air. And the important parts of it are going to be what I tell you to do here. I don't think it's necessary for us to draw a circular dish. Okay? We know in our diagram that this is the air up top, and this is the water. Once again, this is the interface, or sometimes it's referred to as the boundary. We do need to draw in what's called the normal line. The normal line plays a very important role in the formulas we use. When we learned about reflection, the normal line was a perpendicular line to the surface of the mirror. When we talk about the normal line for refraction, it's a perpendicular line through the interface. So it's a line perpendicular to the boundary. The light, in terms of what it is we're looking at right now, is going at about this angle, roughly. And there's light going all over the place from one boundary to the other, but we like to talk about it hitting the interface where we draw the normal line. Okay? I mean, could we just say, well, there's a normal line over here? Yeah. The light would still follow the same path, but we like the normal line to be where that beam of light strikes the surface. And then the important feature is that the refracted beam of light refracts towards the normal. I don't care how tightly you draw it towards the normal. What I want you to understand is that this angle up top, which I am going to call theta 1, is bigger than this angle down here, which I'm going to draw theta 2, or label theta 2. And I'm just moving my beam a little bit so that I can fit that in there so you can see it better. Theta 1 is the angle between the beam of light and the normal line in the first medium. And theta 2 is the angle between the ray of light and the normal line in the second medium. Why is the first medium air and the second medium water? Because that's the order that the light passes through the media in. It goes in the air first, then the water. Theta 1 is called an angle of incidence. And theta 2 is called an angle of refraction. Because of that, sometimes I will make the mistake, I spelled refraction wrong, sometimes I will make the mistake of actually labeling these angles as theta I and theta R. It's just an old habit from an old formula. But 1 is the angle of incidence, theta 2 is the angle of refraction. What else are we asked here? Label the interface we did, the normal line. We got that. The angle of incidence, we've got that, the angle of refraction. And then it says record a variety of data. So we're going to do an experiment together here together. I guess we don't need to say it together twice. We're in class going to do this experiment where we collect the data to find out something about light's behavior in water. And when you take a look at this, and I'm going to be passing it around, on the top, the angle at the very top of this is 0. So if I were to move this beam of light so that it's passing through dead center in the 5, that would be an angle of incidence of 5 degrees. If I were to put it and the laser beam of light is kind of thick, but my eyes at this distance are not great. But if I were to put it so the center of that thick beam of light at the top is at 20, then theta 1 would be 20 degrees. At the bottom, 0 degrees is marked at the bottom as well, so I could read theta 2 by simply looking at this. And you're going to get a chance to look closer at this, but I'm going to try from this viewpoint. That would be theta 1 equals 20 degrees. And would some of you that are close agree that theta 2 is 15 degrees, or really close to 15 degrees? So you're looking down here at the numbers. I might say, and it's kind of a crappy design, oh, it's 15. I was going to say I might say 14. But it only goes up in increments of 5. That doesn't mean when you read this, they're always going to be increments of 5. If it was part way between 10 and 15, then you would have to judge what that angle is by maybe saying 13 degrees. So you are going to, in your table of values, we are going to be using these values for theta 1. This is our manipulated variable. You're going to be using 30, 35, 40, 45, 50, 55, 60, and 65 degrees. So if this were plopped down on my desk and I was supposed to do it for 30 degrees, I would look at this apparatus and I would move the beam of light so that it's passing through the 30-degree mark at the top. And then I would read theta 2 at the bottom. Dua, what would you say theta 2 is there? I know it's not that close to you, but 20? Yeah. Okay. And you have to look dead on. So what I'm going to do is I'm going to put this on your desk and ask you, Is it going through exactly 20, or is it more or less than 20? And I know the water is jiggling around, so the line of light is moving around. What would you say? So this tick where my thumbnail is 20. This tick is 25. Is it exactly at 20? Yes or no? No. So it's between 20 and 25. Is it closer to 25 than 20? Or is it closer to 20 than 25? It's closer to 20. It's pretty close to 20, isn't it? But it's not exactly 20. I might say 22 degrees or 21 degrees. And the purpose of this is not to test anybody's skills in the lab. It's to learn about refraction. So that's going to be our first data point, which is 30. And you're going to tell me now, do you want to go 21 or 22? I don't know. You're looking at it. 22. Okay. I'll be honest with you, that's what I would have said when I first looked at it. So, Shazmaida, what you're going to do is you're going to move this now to 35 degrees up top. And you just hold this and you just move it around. Perfect. And then you're going to read theta 2 at the bottom. I'd say it's 25, yeah. I might, if somebody said 26, I'd be okay with that, but I would say it's 25. You're going to move it now to 40 degrees up top and read the angle at the bottom. And then I'm not going to help you guys anymore. Again, we're not after accuracy here. We're just learning something about this. 28? You pass it back to Amanda, please. Amanda's going to put it at 45 degrees. $33? Sounds good. Pass it over to Tyson, please. Or, yeah, we'll go that way, and then some of you, I'm sorry, will not get a chance to collect data. But we're going to be doing a lab with refraction, I believe, on Tuesday, where every person is going to actually have to use a laser beam to determine angles of incidence and angles of refraction. So you're at 50 degrees, Tyson? 35? By the way, the relationship between the variables here, everybody, is a trigonometric one. And trigonometric relationships are hard to see when you look only at the angles. So don't try to read too much into these numbers. We're going to do some calculations which will tell us how good the data collection or consistent it is. 38. And that's at 55? Can pass it on to somebody else. Doesn't matter. We only need 2 more. So, Evan, you're going to go to 60 degrees. $41. Okay. Again, don't read too much into this. The reason I'm saying that is it appears to be going up by 3 degrees each time, but don't worry about that, okay? And we got one more. Zebby's going to get it, and then he's going to put it on the back counter. Not sure? Okay. So is this at 65? Okay. So I'm just going to get my big head in here. Would you agree it's between 40 and 50?
Yeah.
Would you agree it's less than 45 though?
Yeah.
So now what you have to do is decide if. Okay, yeah, okay, good. Let me just check. Yeah, I'd go 41 degrees. I don't know though. That's the same as the other one, right? Well, let's just go with it. That's what we got. It's data, so we're going to collect it. You would expect these two numbers to be different. So why are they the same? Well, there's some experimental error here someplace. Maybe when Evan read his, he rounded up to 41 when somebody else might round down to 40. And maybe you rounded down to 41 when I could have said 42. It's not important. Okay? We're going to analyze this data in a little more detail in a minute. First question though, in general, what happens to the angle of refraction if you increase the angle of incidence? Well, it gets bigger. I mean, to just look at this one more time, if I ask you to watch the incident beam of light, which is the beam of light at the top, I'm increasing the angle of incidence right now. Now I'm going to do the same thing, but I'm going to ask you to focus on the beam on the bottom, which is an indication of the angle of refraction. And you can see that as the angle of incidence goes up, the angle of refraction is going up as well. It is not a linear relationship, though. You'll find out what the relationship is in a bit. So as theta 1 increases, so does theta 2. Is all of the light refracted when it hits the surface? Well, you might not notice this unless I pointed it out to you, but the answer is no, some of it is reflected. Because if you look at my hand, can you see that light hitting my hand? Some of the light is bouncing off of the surface, and some of the light is refracting into the surface. So the bottom line is some of the light is reflected. And I don't want you drawing this, what I'm going to draw, because it's almost impossible for you to draw showing all of the nuances. But what we have is the following situation. Give me a second to make it properly drawn. We have this situation, but the amount of light that's reflected is quite small. The amount of light that's refracted is quite large, but clearly it can't be as much light as hit the surface. So there's a splitting of the light when it hits the surface. Most of it in this case refracts, but some of it reflects. Okay, remember that if a beam of anything that's a wave refracts towards the normal, then the speed decreases during refraction. So in which medium? Yes, go ahead.
Could you get a refraction of like 100% if you had light entering a medium that had like no albedo?
I don't know that such a substance exists. I think there's always some albedo, which is a way of saying some reflective properties in terms of light to an object. I suppose if we could get some material that light can travel through that's very dark, the distribution is more towards the refraction end than reflection. By the way, you can have all of the light reflect. not by passing light from air to water, and this is just maybe 1 or 2 lessons ahead of us, by putting the light instead from water and attempting it to get into air. And there is absolutely, I want to make sure, there is absolutely 0 light being refracted out of that water and going into the air right now. That's something that we call total internal reflection. 100% of the light will reflect. But it will only work when you go water to air, or attempt to. Have I answered your question? Okay. Which of these 2 media, air or water, is more dense in terms of light? Well, it's going from air to water and it's bending towards the normal, which means it's slowing down when it enters the water, which means water is more dense. The optical density of water is greater than the optical density of air. Which, I don't know. That may kind of make sense to you because water is more dense than air. But don't confuse physical density with optical density. There are substances that have a very low density in terms of their mass distribution, but optically they are very dense. And again, I want to make sure you get this idea before we get to the formulas. The greater the density, the slower the light will travel. It's like trying to slog your way through 2 feet of mud. It's very dense. You have to move slower. So, what determines the optical density is something called the index of refraction. And this is very confusing for some people. Don't confuse index of refraction with angle of refraction. Okay? So what I'm saying here is how much the light bends when it enters a medium is determined by the refractive index of each of the media working together. And indices is plural of index. So there's this thing called refractive index of a medium. Water has a refractive index of 1.33 for most colors of light. Diamond has a refractive index of 2.42. Air has a refractive index of 1.000375 or something, which means air is not very dense at all. But water, which is 1.33, is a lot denser than air. And diamond, which is 2.42, is even more dense than water. Here's how we define the index of refraction. N is the index of refraction, and it's the ratio of the speed of light divided by the speed of the light in the medium. So that C is the speed of light in air or a vacuum. This is not a formula that's on your formula sheet. It's not one that we're ever going to use. I'm using this as an illustration to explain to you what N means. What does it mean if I told you the index of refraction of a substance, of light in the substance, was 2? Well, what that would mean is that if you rearrange this equation, that light in that substance, when we put n equals 2 in, we have to cross multiply and rearrange, will be 1.5 times 10 to the 8 meters per second. Think about this. If n is 2, the speed is half the speed of light. So if n goes up, the speed goes down. Which kind of makes sense because n is a measure of the density of the medium. I'm going to come back to why I had you do this in a second. In the meantime, we're asked, what is the refractive index for light and air? And I've got number 2 up there just because I wanted to show you the formula. If you were to look up the speed of light in a vacuum, and by the way, A vacuum has an index of refraction of 1.00000000000 forever. Because there's nothing less dense than a vacuum. Okay? Air is a little bit more dense. This is the speed of light in air. You don't need to know this. I pulled some information off of the internet. This is the most currently accepted value for the speed of light in a vacuum, and this is the value of the speed of light in air. Is there much difference? Well, actually there's like 90,000 meters per second difference. There's a huge difference, 90 kilometers per second. But when we round things in applied science to 3 significant figures, this becomes 3.00 and this becomes 3.00. If I said, what is the refractive index for light in air, you would have to take the speed of light in a vacuum and divide by the speed of light in air. Let's do that. The index of refraction, and this is for light in air, would be 299,792,458 over 299,702,547. And I don't know what number I said before. I want to change my mind and say it's 1.0023. I think I said 375 before. But we're going to find out. 299,792,458 divided by 299,025. 547. Yeah, 26. Assuming I entered those numbers right, I think I did. 025,547. So the index of refraction of light in air is about 1.0026. Do you get the same number or not? You don't. I obviously entered a digit in wrong somewhere. 299,792,458. 299,702,547. Getting this? Okay, that's maybe a number that makes more sense to me. The index of refraction of light in air is very, very close to the index of refraction of light in a vacuum, which is exactly 1. So now, thank you. So now, everybody, if you were to look up the index of refraction of light in air on your formula sheet, it'll just say 1.00. That's the index of refraction of light in a vacuum or air to 3 significant figures. I'll just show that to you. And I hate this. Index of refraction of air. Air isn't refracting. It's the index of refraction of light in air. And it's 1.00. That's also the index of refraction of light in a vacuum. In reality, it's actually 1.0003. Okay. So now we can talk about the formulas. Let's not worry about why these two formulas are separated from each other on your formula sheet. If you go to your formula sheet and look under light, or waves rather, you will see, kind of near the center of your screen, that n2 over n1 equals sine theta 1 over sine theta 2. And then n2 over n1 equals v1 over v2, which is equal to lambda 1 over lambda 2. 1 refers to in the first medium, 2 refers to in the second medium. So n is the index of refraction, v is the speed, lambda is the wavelength, and of course theta is the angle of the light. Keep in mind that's 6 different formulas. Well, there's a lot of combinations of formulas here. So what we're asked to do in this next question is calculate the index of refraction of light in water. So let's just do a calculation here, but I need somebody's help. I'm pretty sure, I can get this thing to close. I'm pretty sure that this was 22 degrees, I think. Was that right? Okay. So how would we calculate the index of refraction here? You would say sine of theta 1 over sine of theta 2 equals n2 over n1. But n1 is 1.00 because we went from air to water, which means n2 will be sine of 30 degrees over sine of 22 degrees. This will be n of water, or n of light in water. So 1.33. Yes? Nope, I'm in degrees. I need to be in degrees because these angles that we measured were in degrees. Do you get 1.33? You know what? That's pretty good because that's exactly what I told you the index of refraction of light in water is. Take a minute and do your calculations here. I don't care what you write down. We're just kind of in a learning mode right now. Do your calculations with all of this data. And I'm going to calculate n2 from both sets of data at the end. So just pick a couple of random ones and find n2. Sine theta 1 over sine theta 2 will be equal to n2. So the set of data that Evan collected gave 1.32. The set of data that Evie collected gave 1.38. But those are still well within experimental error. I mean, if you compare it to 1.33, 1.38 minus 1.33 is this. If I divide by the theoretical value of 1.33 and multiply by 100, I get 3.8% error. And I don't know that this has come up in this course yet, but high school physics, anything less than 10%, you're doing a good job. Look at this piece of equipment we were using to find our angles. It doesn't even have increments every degree. So getting 3.8% is very close. Bottom line here is these numbers should all be pretty close to 1.33. Okay. The lab that you do next week, you will have an unknown substance that you have to collect data for. Okay, let's get now to the actual working examples. Use your index of refraction found, so it's 1.33. We're dealing with n1 equals 1.00, n2 equals 1.33. Fell a little bit behind schedule here, but had we had time, I would have calculated an average of all of those. But it's going to be very close to 1.33. V1 is 3 times 10 to the 8 meters per second. So what is V2? Which would be the speed of the light in water. We have to use n2 over n1 equals v1 over V2. It's not a difficult application in physics. There's just a lot of variables and a lot of equations that you have to decipher. So I guess we're going to have 1.33 over 1.00 equals 3 times 10 to the 8 over V2. So you're going to take 3 times 10 to the 8 divided by 1.33. I'm going to guess you're going to get about 2.25, 2.26. 2.26 times 10 to the 8 meters per second. When you take a look at number 1, it does tell you the wavelength of the red laser is 650 nanometers. So in question 2, where we are asked for the wavelength in the water, the wavelength in the water is lambda 2. Lambda 1 is 650 nanometers. So we can use N2 over N1 equals lambda 1 over lambda 2. And sooner or later somebody goes, wait a minute, I think Mr. Way, you flipped over the N and the N. No, that 2 over the 1 is the order for N. Everything else is 1 over 2. Because the bigger N is, the smaller everything else becomes. So this would be 1.33 over 1.00 equals 650 nanometers over lambda 2. Nanometers? Why not? It's just a ratio of 2 wavelengths. It doesn't matter what set of units you choose to use. And that means that we're going to take 650 divided by 1.33. And get 489 nanometers. Now, before we finish this off, and we're not going to do the entire next example, we're just going to do one little piece of it. I want to give you enough time to practice these. Any questions with this wavelength? Sometimes somebody asks, and it's a great question, isn't this blue light? That's not red light, it's blue. And yet when you look at the light over here in the water, it's red. What does not change during refraction? Anybody remember what does not change? Speed of the wave changes, the wavelength changes, the frequency. The frequency of both of these beams of light is the same, and that's how your eye works. The frequency takes electrons in the retinal sheath of your eye and causes them to create that frequency, and your eye senses the frequency, not the wavelength. By the way, if you do want the frequency, all we have to do to find the frequency of the light is to take the speed of light in air and divide by the wavelength in air. To get the frequency. If you wanted to, you could take the speed of light in the water and divide by the wavelength in the water. That would give you the frequency as well. And you should get very close to the same thing. So we get a frequency of I'm entering it into my calculator the wavelength as 650 times 10 to the negative 9 because it's 650 nanometers. But in standard scientific notation, that's 6.5 times 10 to the negative 7. It doesn't matter which way you do it. So this is the frequency, 4.62 times 10 to the 14 hertz. Okay. So really, after I printed this handout out, I thought, you know what? I should just change this to the following. A ray of light with a wavelength of that travels from air to water at an angle of 60 degrees to the interface. The only thing I want us to be able to do here is this. What is theta incidence? What is the angle of incidence? Because, for example, if I wanted to find the angle of refraction, I would have to make use of this. Sine of theta 1 over sine of theta 2 equals n2 over n1. And I'm asking you, what is that number? What would you put in for theta 1? Evan?
30 degrees.
Right, 30 degrees. It's kind of a trick question because this says it strikes the diamond at 60 degrees to the interface. So you have a block of diamond. Let's just say this is the diamond. And the light comes in and it strikes at 60 degrees to the interface, but theta 1 is just 30 degrees because those two have to add up to 90. So this is the only point of me giving you this question in your notes, is so that you know to be careful. Theta 1, theta 2 are always measured from an interface. The questions you're working on are attached to your lesson. Numbers 1 to 13 on page 21 for practice. Same thing I've been getting used to in all my classes. I don't look at this as homework anymore. My philosophy is different. It's practice.